All right, let's dive in. Today, we're going to crack open one of the oldest and, honestly, one of the most devastating bugs in the history of computers. It's a flaw so basic, it's kind of like finding out that the front door to every single bank, government building, and hospital was built without a lock from day one. We're talking about the buffer overflow, and its story, well, it reveals this fundamental vulnerability right at the very core of our digital world.
So, to really get this, we're going to start at a digital crime scene, because that's exactly what a buffer overflow is. It's not just some innocent little bug, it's a vulnerability, a weakness that has been exploited to cause absolute chaos on a global scale.
And that brings us to the central mystery here. I mean, it sounds like something straight out of a movie, right? But it's a historical fact. A tiny, almost invisible error in code literally has the power to bring modern society to a screeching halt. So the question is, how is that even possible?
And look, this is not some theoretical problem. This number, that's the estimated damage from just one attack, the SQL slammer worm back in 2003. This thing disrupted bank ATMs, 911 emergency systems, even airlines, all because of this one single type of programming mistake. The real-world cost is just staggering.
Okay, so to understand the crime, we have to understand the unlocked door. This vulnerability, it isn't really an accident. It's actually a consequence of a huge design choice made decades ago. A trade-off, really, between raw, blistering performance and built-in safety.
This right here lays out that core conflict perfectly. On one side, you've got languages like C and C++. They were built for pure, unadulterated speed. They give programmers direct, hands-on control over the computer's memory. On the other side, you've got languages like Java and Python, which act kind of like a protective parent, managing all that memory for you. So C basically hands you the keys to a Formula One race car, but with no seatbelts and no guardrails.
So you might be thinking, okay, why should I care about some decision made for an old language? Well, here's the thing. C isn't just an old language, it is the language. It's the bedrock, the foundation that our entire digital world is built on. The operating system on your phone, on your computer, the servers that run the internet, so much of it has C deep down in its DNA, which means its vulnerability is, in a way, everyone's vulnerability.
So here it is, the unlocked door itself. A buffer is just a temporary storage spot in memory. Think of it like a small box designed to hold exactly 8 letters. A buffer overflow is what happens when someone tries to shove 20 letters into that box. The extra letters don't just vanish. They spill out and overwrite whatever was sitting in the memory right next to the box. And that is where the chaos begins.
Now that we know what the vulnerability is, let's get to the fun part. How is it actually exploited? This is the heist. How does an attacker turn a simple data spill into a full-blown takeover of a system? It all starts with a part of a program's memory called the stack. You know, inside every running program, there's this structure called the stack. Think of it as the program's short-term memory. It holds temporary data and stuff, but most importantly, it holds something called the return address. This little piece of data tells the program where to go after it finishes a task. It's basically the program's GPS, and for an attacker, it is target number 1. So this is what a healthy, happy stack looks like. You've got your temporary data, your local variables, sitting neatly right next to that all-important return address. Everything's in its proper place, the program knows exactly what to do and where it's going next. Simple. But this is the attack. The attacker sends way too much data into the buffer. See all those A's? That data spills over. And crucially, it overwrites the original legitimate return address. And in its place, the attacker writes a brand new address, one that points directly to their own malicious code. So the attacker's plan is simple, but it is devastating. Step 1, they write some malicious code. Step 2, they stuff that code, along with a bunch of junk data, into memory, using that buffer overflow. And step 3, they hijack the program's GPS, that return address, and make it point directly to their code. The program, just thinking it's following normal instructions, willingly turns over the keys and runs the attacker's commands. Game over. And believe me, this is not just theory. This exact technique has been the engine behind some of the most infamous cyber attacks in history. Let's take a look at 2 particular worms that use this exact unlocked door to shake the internet to its very core. We're going to look at 2 huge milestones. First, the Morris worm in 1988, which was basically the internet's first big wake-up call. And then SQL Slammer in 2003, which showed the world a terrifying new level of speed.
And you guessed it, both were powered by buffer overflows.
I mean, just let that sink in for a second. In 1988, when the internet was still basically in its infancy, a single program written by a graduate student managed to infect 1 out of every 10 machines connected to it. It was the very first time the world saw how one tiny vulnerability could have this massive cascading effect across the whole network.
Now, fast forward 15 years. The same technique was used again, but this time the result was even more dramatic. SQL Slammer wasn't sneaky or subtle. Its defining feature was just pure, unadulterated speed. And the efficiency of this thing was just stunning. The entire piece of malicious code was only 376 bytes. That is smaller than a simple text email. It was tiny, it was elegant, and it was unbelievably destructive. With that tiny little payload, it managed to infect at least 75,000 critical servers that were running Microsoft SQL. And we're not talking about home PCs here. These were the backbones of businesses, of infrastructure. And here it is, the final, absolutely mind-blowing number. It did all of this, infecting 75,000 servers in less than 10 minutes. At its peak, the infection rate was doubling every 8.5 seconds. It was a digital pandemic moving at the speed of light.
But, okay, the story doesn't just end in disaster. These attacks, as bad as they were, served as a really harsh lesson. They forced the entire software industry to get serious, I mean really serious about security. We started building a digital fortress to defend against these kinds of attacks.
In response, the industry came up with several key defenses. We've got things like data execution prevention and address-space layout randomization, but I want to focus on one particularly clever idea, something called a stack canary.
The name is actually pretty cool. It comes from the old practice of using canaries in coal mines to detect toxic gas. In software, a canary is just a small, random value that gets placed on the stack right next to that critical return address. It acts as a perfect digital tripwire.
And here's why it works so well. The canary's value is totally random and unpredictable. For a buffer overflow attack to actually work, the attacker has to overwrite the canary just to get to the return address. But here's the clever part. Right before the program uses that return address, it checks the canary. If the value has changed, even by a single bit, the program knows it's under attack and just shuts down immediately. It stops the attack cold before any malicious code can ever run. It's a simple but incredibly effective alarm system.
So, we've learned how to lock this particular door. Defenses like stack canaries have made these classic buffer overflow attacks much, much harder to pull off. But the bigger story here is about the constant cat and mouse game of cybersecurity. And that leaves us with one last question to chew on. Our defenses are smarter than ever, for sure, but what's the next unlocked door hiding somewhere deep in our code?